I will take at SSC, because as we had seen that this is going to make a foundation for your applied physics courses that you will study in several disciplines later on. And hopefully that along the way you will learn many other skills that are transferable not only towards courses in engineering and science, but also in general where you come across solving different problems. So today we will begin by an introduction to this course, what this course is going to be, what are the grading schemes, and other rules and logistical stuff that you have to follow during this course. One thing I would like to say that please try to come before 4:30 every day. It's very disturbing when people keep on walking, but of course there can be delay, you might have to get out or something. So after the class begins, this door will remain closed. You can get in and get out from that door if you have to. So this course has an enrollment of about 275 people, and we have also divided it into 4 recitation sections. So already 3 recitations have taken place, and most of you know how the recitations are going to be. Today I will have to say a little bit more about those recitations and also these lectures and other stuff. So I'm waiting for people to arrive. So we have chairs on the side. You can also take them. The capacity of this room is about 300. So you can leave the seats empty at the end. And also another advice for people with glasses that try to come a bit early so that you can sit closer to the board. I will try to write it in as bigger font as possible, but I'm used to, like most other people, writing a bit smaller just to focus on people here. So some people might have trouble in viewing what's written on the board. So if you have those visual problems, please try to come earlier so that you can sit closer to the board. Okay, so let me begin by an introduction of this course before we. So this course is modern physics, and it has 3 major components. Special theory of relativity that we have added this year, and mostly it would be quantum mechanics. I'll say more about what quantum mechanics is, and it would have a little bit of thermodynamics. This part of this first lecture will be focused on my motivation for you to take this course, and also I'll try to sort of put it in larger context, why this course is being taught to all of you, even those of you who not have to go towards science and engineering. And we'll also say something about course contents and logistics and some rules, and then we will have some feedback forms to fill in for the purpose of this course. And then we'll begin discussion on real topics. So this woman in yellow jacket with glasses, could you please stand up? Yes, I'm looking at you. Yes, please stand up. So what's your name? Reja. Reja? Reja. So why are you talking?
Yes?
Why are you talking?
Asking about what's written on the board because not very clear.
Could you please say louder?
Asking about what's written on the board because not very clear.
What's written on the board?
Yep.
There's nothing written on the board.
So now I know.
Yet.
Yep.
So people at the back, I would like to request your cooperation. Please try to switch off your talking. Okay. So let me begin this thing by recounting what I have collected are the big successes of past 1 to 200 years of what people have done. So number one comes to my mind is the electrification of the world. You see these giant poles and electric wires hanging on them, which are taking electricity from power stations to the cities and everywhere in the world, and then they are powering everything in our homes, in universities and schools. This wasn't there 100 years ago. It started around 1900, initially in the United States and a few European countries, and then in the past 60 to 70 years, it has spread almost everywhere in the world. So this is one of the biggest success or engineering feat of the past century. The next one perhaps is in the transportation sector. In just about the last century, the transportation has been revolutionized. For maybe millions of years of our existence in this world, when we evolved into humans, chemical engineers, mathematicians. So most of the successes of last century, if you just think broadly, they are sort of the result of specialization into one particular area. Sorry? Yes, so the optimization algorithms and game theories, chaos theories, probability theories, they are behind that. So there are emerging applications which require more than one, but most of them, they are specialization in one area. But if you look on future challenges, what people are supposed to do, or what are the things that are probably going to be happening and requiring engineering and scientific solutions, I have listed a few of them. For example, I can think of smart appliances in homes, in our pockets, in offices that are doing stuff automatically just according to the psyches and needs and quirks of individual people. That they have to not only do some mechanical, electrical stuff, they have to customize it to almost every individual. It includes a customized educational needs of everybody else. Maybe 50 years from now, everybody is just learning a part of their curriculum by sitting, interacting with some robot or some other thing, which is teaching that person, which is in line with that person's need. Because everybody learns in a different way, which is actually one of the biggest challenges in this class, because there's a whole spectrum of people sitting here. So this is one of the needs of the future. Maybe another one, computers that do science and engineering and all these things that we have been doing for ourselves. They're kind of thinking computers. They're doing research, coming up with different solutions to the problems of the world. And this includes, let's say, examining a patient and prescribing the medicines and maybe simulating the effect of medicine even before you administer the medicine to a patient to see what are going to be its effects, side effects, given the genome of this particular person. So it's going to be at a level that is not seen in the last century. Artificial intelligence, yes, you read my mind, it's the next part. So we need machines that are capable of learning on the job. You design a multi-purpose thing and you put it into an environment and it learns how to deal with that environment quickly. Just like humans, like we don't do that quickly, but for example, you put people in a certain situation over the course of years, they learn to adopt to that thing. But we need, in the future, we might need machines that do that thing quickly. So they learn on the job, which is called machine learning or artificial intelligence. Other things, customized medicines, healthcare, customized educational strategies, customized syllabus, and maybe customized content. So these are the things that probably have to happen. Maybe few things, secure internet, which would be based on quantum cryptography, because now you can eavesdrop and read information. We will be needing much faster computers, which would be based on quantum algorithms. So this course comes in there. we will be needing new algorithms to solve problems quickly. So quantum-based computer will be needing code that can solve problem in a much quicker time than the usual algorithms. So all those programs that have been accumulated over the past 50 years might have to be translated into another form where those things can be done quickly. We have been able to do interplanetary transport, but we would be needing maybe intergalactic transportation to go to other galaxies, or maybe to go to near other stars. We would be needing materials which, let's say, are self-healing. They are changing properties according to the needs of a given situation, and they would have to be designed at atomic level. So these are maybe one of the things. And doing all of these things while making sure that our actions don't result in a climate change that is catastrophic of us, and we also have to reverse the damage that we already have done. In fact, if you go on the web, World Economic Forum, UN, anywhere you search what are the biggest challenges of the next 10 years, 20 years, the climate change comes on the top. And all of these things, I hope you can appreciate, they require expertise that are not in one domain, that are in several domains. So this can be a combination of experts, and also those experts have to be somewhat well versed in other things. For example, a computer scientist writing a code will have to know some quantum electronics of the computer that he's working on to know what are its possibilities that we can code into. Like most of the digital computers that we are working now, even we don't know, they design, for example, the transistors and diodes that are making up the chips in the computers, they are working according to a quantum principle. But at a bit more higher level, since it's ones and zeros, still we are working with the old digital logic. So we have to program according to that. But once new computers comes in, so people have to know different things. Similarly, if you want to design something that, let's say, is doing stuff according to psyche and needs of user, you have to have experts that are not only expert in machine, but also in, let's say, psychology. So most of the other things, all of these and many other big things that are going to happen in the future, they require people that have transdisciplinary skills. And that was actually one motivation for the establishment of this school at SSC, that its aim is to carry out a world-level multidisciplinary education and research with where we call it no boundaries concept, that the boundaries have to be fuzzy. A person studying in, let's say, computer science have to know a little bit of biology, a person studying in biology has to know a little bit of chemistry, and so on. So that's why in your first year we teach you a variety of the courses, and this modern physics is one of that thing. So actually this particular course is more than that, because most of the applied science and engineering, it's going to be dependent on the knowledge gained in this course. So for example, one of the aim is to have multidisciplinary research and to solve problems and anticipate the needs of future, and hopefully become a doorway of opportunity for region and beyond. So this was a kind of motivation for me, from my side to you, if you are not motivated enough, that the structure that we have at SSC is different from every university in Pakistan, and it's in line with leading universities in the world only because we want people to be trained for future, and not just people who are doing stuff in their silos, who make a mandate जो है ना वो नहीं हम बनाना चाहते in another way. So that's why we have this multidisciplinary education in the first year, where this course also fits in. So let me now come to the nitty-gritties of this course. So this course will have three basic components. One is what are the laws for very fast moving bodies. So you have studied classical mechanics, in which you have studied how the bodies behave, how to move a body, how to stop a body, how to predict the motion, circular motion, linear motion, and you did that according to Newton's laws. But implicit in that course was this thing that the bodies are not moving fast enough and they are not small enough. even though it was not spelled out that much for you. For example, if you go to an atom or molecule or a few molecules together, those Newton's laws are, and the concept that we have studied, the concept of conservation of energy, concept of conservation of momentum, concept of conservation of mass, that's not going to be applicable as it is. It's going to be changed. Not only for small bodies like at the atomic and molecular level, but also for fastly moving bodies. So the laws have to be modified, and that's what this course is going to be. That we will generalize what we have learned in mechanics, that includes a discussion of fast moving bodies, and from very fast I mean things that are moving closer or maybe a fraction of speed of light. So our you can say standard for measuring the fastness is the speed of light. And on the other hand, we will learn the laws that govern small bodies. For example, molecules, atoms, that what are their structure, like this wave-particle duality. I'll get into more detail later on in the course. But for now, you can think of this thing that fast-moving bodies, which is the special theory of relativity. We will learn the generalization. And in the meantime, we will also see how this specializes to Newton's laws when we take slow-moving bodies. And then we will study the laws that govern small bodies. And we will also study the laws that govern a lot of bodies. For example, if you think of a gas, you can think of it as billions and billions of small molecules going around. So the ideal gas law that you have studied, PV is equal to nRT, or other relation that you increase pressure, volume decreases, and also the second law of thermodynamics, we will derive them from the probabilistic nature of this law of large number of bodies. So this thing actually relates to the statistical behavior of molecules in a fluid. So we will study the basic laws of all of these three, which will enable us to study their applications in, let's say, nuclear physics, molecular spectra, how you can understand the molecular nature, material properties, quantum computers, semiconductor theory, lasers, stars, and evolution of universe. So, all of this, when we will be doing, we will be generalizing the laws of mechanics that we have already studied. And at some time, we will be approximating the laws that we learn here and see that in the approximate way, they reduce to the laws that you are already familiar with in mechanics. That's why we started with Taylor series. That if you have an exact function, when you approximate it, you get how to approximate. That's what we are learning in recitations. So one reason is this, that when we will have general laws here, when we do the approximation, they should reduce to the classical mechanics laws that we are familiar with already. The one important thing in this course is going to be this difference from the common sense. Newtonian physics or classical mechanics that you have studied in last semester, the results are very much in line with what you think should happen. If you throw a ball a bit higher, it should go higher and come back. We are already familiar with this thing. If you throw like this, it looks like it goes in parabola. That's what we learned in projectile motion. But here, what we are going to learn is going to be counterintuitive. And it will not be in line with your everyday experience. Because in everyday life, we don't come across with bodies that are moving very fast. We don't come across with bodies that are very small. Our experience is based on very special and a very small domain of motion and the size of the body. So that's why whatever we will learn here would not be in line with our everyday experience. Yes, please. Okay, so the question is that will we learn these quantum mechanics through the quantum field theory or through the atomic particles? So quantum field theory, we won't be able to go that far. That's a course that's about 200 level above this course. We will be studying with reference to smaller particle like atom, electron, proton, and unmanned. So any other question about the course contents so far? So you get an idea what we are going to be covering in this course. Laws of fast body, fastly moving bodies, small bodies, and in this part, the laws of a lot of bodies, where there are trillions of atoms and molecules in a gas or a liquid, what we can infer on the average properties of those substances. Okay. So here comes the part that many of you care most about. So we will have homeworks, 12% quizzes, 18%, there will be around 12 to 14 quizzes, one quiz almost in every recitation. There will be 2 midterms. The first midterm would be 10%, and the second would be 20% of the course. And there's going to be a final examination, which will be 40% of the course. So essentially, the weight of the exam will increase as we go along the semester. Okay, so here are the policies about missed exam, because some of you are going to miss the exam definitely because of some reason. So if you miss a quiz, you will get a 0, unless you have an approved petition from the Office of Students Affairs. In that case, you will get your own average in your other quizzes. No cross average in any missed exam. You will get your own average in other quizzes. If you miss a midterm, so if you miss the first midterm, you will get the marks in that midterm based on your next midterm. And there will be a 20% cut if your petition is not approved, and if your petition is approved, you will get with the same percentage as you get in the next midterm. So since the second midterm is double the first midterm, you will get 40% if your petition is not approved and 50% if it is approved. If you miss your second midterm, you will get the marks in the second midterm based on your final exam. If you miss final, you're almost out of the course. That will have to be rearranged if there is some general reason. For homework, a missed homework will be a 0 unless you get an approved petition that for 1 week or 2 weeks you were busy somewhere, and you will get average based on your other homework. So whenever you miss an exam, it's going to be an average based on your other exam of the same type, essentially. So no class average for any missed exam. So this is to make sure that things remain fair. Okay, and here is an example of my previous grading, because in the last time when I taught this course, the most asked question to me was not about the course. It was, what mean do you give on, what grade you give on mean? Okay, so here's your answer. The mean is 64, and the B plus starts at 65.29. So the answer to the question, what grade you give on the mean, is B grade. So from 62 to 65. And here you can see the percentage distribution. Most people are getting B grade, and still a lot of people are getting A grades, and fewer people are getting C and D and F grades. So the trick for you to remain in this part, if you are aiming for the higher grade, and if you're just trying to go through, the trick for you should be to remain in this region and avoid this part of the course. Okay, any question about this grading mechanism? Yes?
Do we have any n-1 form of policy?
No. No n-1 on anything. If you miss an exam, it's gone. You get a 0.
Not for homework as well.
For any, nothing. There's no n-1 on anything. You have to do work for the semester. Individual. The homeworks are going to be individual. Okay, so one warning about homework grading and quiz grading. For homework, we will only see if you have attempted the problem fully and all parts of it, and you will get full marks. But to make sure that you have attempted the problem correctly, you have to go through the solution which we will put on LMS. So it's possible that I repeat the same problem from homework in an exam, and if you do in the same way as you did on the homework, but on a homework you got full points, you cannot argue that I should be given full points again. The exams would be graded very carefully, that you will get points only if you have done them correctly. Because we will be getting a lot of homework, we cannot really see each homework that if the problem has been done correctly. But we also want to make sure that you do some practice, so there will be homework, but the grading of homework will not be an excuse for the same grading on the final exam or on the midterm. So after you get your grades on homework, you should see the solution to see that if you have done correctly on your homeworks or not. So here are a few other set of things. So the first thing is about class lectures. We have a course textbook, this non-classical physics beyond Newton's view. It's written in the outlines, which is uploaded on the LMS. So but the lectures will not really be the exact repetition of the textbook, and there won't be any lecture notes. Okay? And it will sort of, the flow of topics would be similar, but maybe another way of presenting the same topics. So you have to be, you should be taking notes, I think, during the lecture, because it's not going to be repeated there. And sometimes the method and derivations would be different. Another important thing about lectures, I won't be doing derivations completely in the class. That, let's say, if there's a problem, I will set it up, write the basic equations, and then I will tell you that, okay, if you use these 2 or 3 equations, solve them together, you get this final result. That part I will be uploading on LMS. All the detailed derivations would be there, so you have to go through them yourself. Because in class, it usually becomes very boring. I'm plugging this equation there, taking that. I'll be doing some of that, but not all of it. So what I'm saying, that there won't be any notes for that from my side, but what I would be skipping, I will be putting that in notes and uploading an LMS. So you can say that 70% of lecture would be here and 30% usually would be uploaded in an LMS. So you will have to complete it with that. Another important thing about lectures. So what we study in the lectures in this week, we are going to be having recitations on Monday and Tuesday and Friday next week, which would be based on this. So there will be quizzes based on these lectures in that week. So you have to be just along the class. You can't leave, like say, 1 or 2 weeks lecture behind, or you will do it later when the exam comes. Otherwise you will be left behind in the recitation. Yeah? Sorry? What information you want me to repeat? Every recitation will have 1 or 2 quizzes. Yes, of course. There won't be any quiz inside the lecture. Because you see 300 people are sitting here, we can't have a quiz, right? So that's why we have actually divided into recitations to make sure that there is more interaction and we can also have quizzes. Okay, the next part. So this is again something about lectures. That lectures will have more to set up the topics and tell you why we are studying this, where it is applied, and the general concept behind that topic. But the derivation again would be on LMS. And some derivation will be relegated to homework, where I will ask you to do those derivations yourself. Okay, and homework will have a little bit more mathematics than what we cover in the class. Okay, and this is something that I have already explained in the recitations. And again, let me stress this, that quiz is a bad word for what we will be doing in the recitations. It won't be a quiz, it's actually a class activity. that I want to experiment in this course, but we can do in this big class. So that's why I have divided you in 4 groups, where we will have a few 4 or 5 TAs helping you. So the idea is that you go through those problems and struggle with them over there. You ask for help, usually after every problem we will be solving that on the board in the recitation. So hopefully your learning would be a little bit quicker that way. Because I have experienced this thing over last 12, 13 years that I have been teaching, that people usually don't learn by lecture. We come here every day, blah, 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 for 1.5 hours, you are getting bored there, and in such a big class. Then people usually learn only when they do something, and when they do something wrong, they are told that it was wrong here and they correct it, and then they remember it. So that's why I have divided you in recitation, so that we can do that feedback process over there. You do something, you ask for us, okay, I'm stuck here, and frankly, in just the 3 recitations that we have, it was very revealing for me, because simple thing that I thought maybe f of 0 means that you put 0 in place of x in, let's say, sin x. Some people don't get it. And for some people it's very easy, but to make sure that everybody goes along, we have that recitation and that structure. So hopefully by the end of the course, we'll see what the result of that style is. Okay, but we don't only have recitations, we will also have tutorials. Tutorials are the optional classes. 4 or 5 tutorial session would be there, where the almost same thing would be repeated, where TAs will come with 2-3 problems related to the topics that we will be covering in the previous week, where they will solve the problems so that you get an idea what type of problems are going to be on the midterms and finals. So to prepare you for the mids and finals, and also like for similar problems on homework, we will be doing those extra problems in the tutorial. So you should be coming to them if you want to go to the higher level in the grades. Okay, so this is an important thing which I usually state up front. In the mids and final, I always put some problems from homework, tutorials, and end of chapters in the book. So my goal is that 60% of final and mid exam should be based on these things. So it's seen. So, but of course, it may not be exact repetition, it will be similar. So if you do homework, tutorials, recitations, and most of the end of chapter problems, you should feel yourself to be in B+ or A- category, if you have good understanding. There will always be 1 or 2 problems in these ones that would be reserved to distinguish people in the upper category. So that's how the exams are going to be. And since many people take some time to learn and to see really what type of problems are going to be, that's why I have 2 midterms. So the first midterm, which is only 10%, will give you an idea of what is going to be the major exam, the second midterm and the final exam. Okay, so any questions so far? The first midterm would be in the 5th week, the second would be in the 10th week, and they would both be cumulative. The second midterm will have everything from this lecture to that lecture. So it's not that second midterm will cover only the part after the first midterm. It is 20% only because, so essentially the second midterm is really the midterm. The first midterm is just kind of a practice midterm where you get to know that what's going to be coming on the midterm and the final exam. For communication, you can always send me an email. Please mention the PHY-104 either in the subject or somewhere in the email, because I have a filter in the email so that goes to a special folder where I know that this email is coming with respect to the course and I can respond quickly, because I get a lot of emails every day. So if you don't distinguish it, the response might be delayed because it can be buried in a lot of other emails. So please include that in the final exam, in the email. So now I have a few feedback forms that I want you to fill. Is there any tears? Please go and give some of Okay, so the forms are an attempt from my side to know more about you, that what type of groups we have, so that I can tailor my lectures accordingly. Other projects from here. So if there are extra forms, please bring them here. Tell some people on If you haven't gotten the form, please raise your hand. So if you're done, please pass to a person on your left. fill form to the person on your left so that we can collect them. Get back to the learning mode. Okay, so a couple of you have asked a few questions. One of them is that would the tutorial questions be uploaded on LMS? The answer is yes. Most of the stuff that we would be doing would be uploaded on LMS, except most of the lectures. Because in lectures, I was trying to be motivating you about the topic and telling you where it can be applied, and then it's really hard for me to write and transcribe everything in that. So that would be on LMS. Everything else would be on LMS, except of course recitations. Because in recitations, since it's coming one after the other, I will have similar level of problems. But of course, the quiz problem, unlike this week, where I have almost the same problem for all of them, would be slightly different from one session to another session, so that as we progress from Monday to Friday, the level of difficulty slightly increases. But again, in recitation, it's not the idea it's not my idea to actually grade you or judge you. I want to give full 18% of those quiz marks in the recitation to everyone. Because the idea of that is to make sure that every one of you at the end of recitation has understood and done the problem correctly and completely. So they will be slightly different, but again, in every one of them, we will be working with you to make sure that all of you learn and do it. Okay, so let me now begin our course. The first thing that I would like to do is begin with the laws governing the fastly moving bodies. And before I do that, let me recap what is called Galilean relativity. So Galilean relativity are the underlying assumptions that scientists have been making about how the universe behaves, from antiquity until about the beginning of 20th century when Einstein changed it. And there were two fundamental principles that were guiding Galileo, Newton, Maxwell, and many other scientists when they were trying to discover the underlying laws that were governing the nature. Let me write the easier and perhaps more intuitive one that they all had. The first was time is same for all observers. It doesn't matter if you are sitting on a horse and running, going very fastly. If you have a stopwatch, of course people didn't used to have stopwatches, let's say in Galileo's time, but there was an underlying assumption that the time as you measure and a person who's standing, let's say, on Earth, when he measures the time is the same. The time interval between two events as measured by somebody standing on Earth and somebody riding in a cart is the same. That was the one basic underlying assumption that they have all been making when they were trying to guess what are the laws that are governing the nature. That's one postulate of Galilean relativity. The other one is actually more, I would say, daring. But that's what humanity had made, and so far as we have been able to see into the universe, we seem to be finding that it's true. It's called covariance principle. Actually, in most of the books, it's written as a principle of relativity, but covariance principle, but I will write it as covariance principle. Because relativity is coming in the name of theory, so I would like to have a different name. So most books would write it as principle of relativity. What does this principle in a layman sense says? That the laws of the universe are the same everywhere. We haven't been to, let's say, personally beyond moon, and our spacecrafts have just left the solar system, but we assume while we are trying to guess the laws and evolution of nature and stars that are millions and millions of meters, or maybe several billion meters and several million light years are away, we are assuming that the laws of nature here and the law of nature there is the same. Or you can put it in a more, let's say, jargon-oriented way, that the laws of nature are the same no matter what inertial frame you are in. An inertial frame is a frame where Newton's first law holds. Inertial frame. So a more, you can say, scientific statement of this principle is that the laws of nature have the same form. They are covariant. The term is used covariant, so that they have a same form in all frames. A frame attached to me while I'm standing here, a frame which is attached to, let's say, a spaceship which has just passed by, or maybe a frame attached to an air molecule which is going like this, or a frame attached to some spaceship which is going at the center of galaxy, or maybe somewhere else. As long as the frame is inertial, so this is the definition. As long as the frame is inertial, the law of the nature have the same form. The quantities can be different. Hold on, please. The quantities can be different, but the form is the same. From the form, it means that, let's say, force is proportional to acceleration. You can measure maybe different acceleration, maybe and there's a proportionality constant of mass, maybe mass is different. Similarly, about the law of gravitation, you multiply two masses, 1 over r square, you get this thing. Or other laws. So while we are trying to discover laws, we are assuming that the laws are the same for all observers. Yes, please.
So, the laws of nature, you said, should be same in all inertial frames. But we are observing them on Earth, and Earth having some acceleration cannot be in inertial frames.
Okay, good question. So there are two parts to this question. The one is that we are postulating that the laws of nature are the same in all inertial frames. That's our underlying assumption, which have so far been found true in a lot of cases. The second part is that Earth is not an inertial frame because it's accelerating. Absolutely correct. When I was first referring to Earth as an inertial frame, I was assuming that we are neglecting its acceleration. But to be true, it's extremely hard to find an inertial frame in universe unless you're floating in upper space. Even there, we get into trouble because of gravitational field. But to an approximation, let's say this room is quite a good inertial frame if we neglect its acceleration because of rotation of Earth. So you're right. In actuality, the laws should have the same form in inertial frame, but if the inertial frame is approximate, it would have an approximate same form. But the idea is simply as this, that the form of the law for one frame and for another frame is the same. These have been two guiding principles while finding the laws of nature. The first one is that the time is the same for all observers. That time measured between two events by an observer, let's say if there are two rail cars that are going in parallel, one is running faster than the other one. In Galilean relativity and until 1905, people assumed that the time as measured in one train is the same as measured in another train. On the other hand, if there are two clocks which were synchronized when the train started from the station, they will be running with the same speed, with the same quote-unquote speed, that they have the same rate, even if the trains are moving with different speeds. And if the both trains are inertial frame, which means that if there is this one train, which is, let's say, going with some velocity, and then there is another train, and since everything is relative, let me assume that this is, so this is going with speed v with respect to this, so let's say this is faster and this is slower. So if we have only two observers here and here, and this is going faster, we can express the situation in two ways. Either by saying that this is going this way with velocity v, or we can say, okay, we imagine that this is stationary and this is going with velocity minus v, that is going backward. So the idea of Galilean relativity is this, that a clock running here and a clock running here, they both have the same rate. And if they're both moving with constant velocity, which means that they're both inertial frame, you can do an experiment in one of them and they will both look exactly the same. For example, if I throw a ball up, it will come down and it will take same time in going up and down if the same force is spent. And if the same experiment is repeated here, it's an exact replication of what is happening here. Even though its speed is different from its speed with respect to a third frame. Maybe somebody standing on the railway station, if I'm allowed to assume that railway station is an inertial frame. Yes? Q? Time dilation. Okay, we are not getting to that. So I'm assuming that we are living in the time of Galileo and Newton, and maybe even until 1900, when the speeds of the trains were not fast enough to detect that time dilation that we'll get into when we get to the special theory of relativity. Okay? So, and similarly, if you discover some law, it will have the same form here, will have the same form here. Maybe the quantities are different, but the form of the law is the same. So these are the two things, and you have assumed them actually while you were doing mechanics in the last semester. But these things which have some prediction, and one of the easier prediction of this thing is this. So let me say we are still in Galilean relativity. I have one frame, let's call me S. I have another frame, let's call it an X prime, Y prime. So suppose this frame is moving with velocity v with respect to this frame. So what happens that if there is some object which is moving with velocity, let's say u prime, if we want to find the velocity of that object in this frame, we can use these principles in this way. So first of all, we know that if here's time t prime, the time t here is the same as t prime. This is the Galilean relativity. Since it's moving along x-axis, so y prime and y and z prime and z are the same. The only thing that is going to be measured differently by both observers is the x coordinate. And the difference can be found from here. Imagine a point, let's say, which is fixed in this frame. अगर आप इसको ट्रेन इमेजिन कर रहे हैं ना, और ये आप बंदा अज्यूम कर ले रेलवे स्टेशन पे, with the pinch of salt that the railway station is inertial frame, even though in the true sense of word it's not. But let's neglect earth rotation. तो जो इसका जो कोऑर्डिनेट है y कोऑर्डिनेट, अगर ये दोनों अलाइंड हैं तो वो वही होगा जो इसका y कोऑर्डिनेट है. लेकिन इसका जो x कोऑर्डिनेट है वो देखें इसके अंदर तो फिक्स है. ट्रेन के अंदर फर्ज करें ये कब पड़ा हुआ है तो उसका कोऑर्डिनेट चेंज नहीं हो रहा. लेकिन एक बंदा जो रेलवे स्टेशन पे खड़ा है वो देख रहा है कि कप अभी यहाँ था, अब यूं चलता जा रहा है. और उसके कोऑर्डिनेट के लिए वी कैन राइट एन इक्वेशन वेरी क्विकली दैट x इज नथिंग बट x प्राइम प्लस vt. अब t प्राइम लिख ले, t लिख ले, doesn't matter because t and t prime are equal. So this is the law of coordinate transformation under the Galilean transformation. That the coordinate of a point in this frame is changing in this frame and is given by this. So this is called Galilean transformation. And this relates the x coordinate of the two frames. Is there anyone who doesn't understand this equation? Okay, good. So let me rephrase it, and if you don't, we can ask you why. यहाँ पे कोई point है, उसका कोई coordinate है. आप इसको train imagine करें, तो train में किसी seat पे कोई चीज़ पड़ी है. तो उसका जो x coordinate है, x, y, z बल्कि सारे coordinate वो fix हैं. They're not changing with time. क्योंकि train के अंदर जो observer है, उसको लग रहा है कि वो चीज़ उधर ही पड़ी हुई है. लेकिन अगर ये फ्रेम हम अज्यूम करें रेलवे स्टेशन पे खड़ा एक बंदा है, उसका फ्रेम उसके साथ अटैच है, तो वो जब कप को देखता है तो जब ट्रेन बिल्कुल सामने थी तो कप इधर था या पॉइंट जो भी है, और जो टाइम गुजरता जा रहा है वो पॉइंट यूं मूव करता जा रहा है. और वो एक टाइम में कितना डिस्टेंस ट्रैवल करता है? vt डिस्टेंस ट्रैवल करता है. तो इसका मतलब है कि इस पॉइंट का जो कोऑर्डिनेट है, इसके अंदर वो अगर x प्राइम था तो इसके अंदर वो चेंज हो रहा है और वो इंक्रीज होता जा रहा है because it's moving like this. अब समझ आ गई है? So I'm going to come to that later. अभी मैंने फिक्स पॉइंट लिया. अब u प्राइम, अब फर्ज करें वही पॉइंट जो है it starts moving with some velocity. ट्रेन के अंदर मैं एक बॉल थ्रो करता हूँ, उसकी कुछ वेलोसिटी है, let me call it q प्राइम. और बाय द वे ये वेलोसिटी क्या होगी? ये होगी dx प्राइम by dt अगर बॉल जो है वो x एक्सिस के अलॉन्ग जा रहा है. इट्स अ रेट ऑफ चेंज ऑफ इट्स x प्राइम. अब इस पॉइंट को वही जो फ्लाइंग बॉल है उसको अगर आप स्टेशन से देख रहे हैं तो उसकी वेलोसिटी क्या होगी? कुछ होगी. Of course, in general we can assume it would be different from this, and we can find this velocity simply as dx by dt. और अगर मैं यहाँ से दोनों का रिलेशन फाइंड करना चाहूँ तो जो गैलीलियन ट्रांसफॉर्मेशन है इससे आराम से निकल आएगा. आई कैन डेरिवेट ऑन बोथ साइड विद रिस्पेक्ट टू t, सो वी गेट dx by dt is equal to dx prime by dt plus v, which gives us u equal to u prime plus v. A very common sense equation. अगर आप ट्रेन पे खुद ट्रेन जा रही है आपकी वेलोसिटी से 20 किलोमीटर पर सेकंड, अगर मैं एक बॉल फेंकता हूँ जो मेरे लिहाज से 30 किलोमीटर पर सेकंड जा रहा है, तो जो बंदा रेलवे स्टेशन पे खड़ा है उसको उसकी वेलोसिटी कितनी नजर आएगी? 50, because it will add both velocities. So this law of velocity transformation, बड़ा लंबा नाम है सिंपल सी इक्वेशन के लिए. This comes from this underlying Galilean transformation, which comes from this assumption of constancy of time for both. So t prime जो मर्जी लिखें, it's the same thing. So this is the consequence. The Galilean transformation are actually never true. We know this today. But until 1905, in the region when you were studying classical mechanics in the last semester, in that regime, they are assumed to be true. So let me put this in historical context. So until 1900, it was thought that this is true. So put yourself back at the time when Bengal was separated into two parts in 1905. So before that time, people thought that Galilean relativity and Galilean's ideas are correct, that the time is measured by the same. And you can actually forgive them if you know how people used to measure time. How did Galileo measure time? Stopwatch. There were no stopwatches. Sorry? Sunrise, maybe. But in most of his experiments, you will be amazed that he measured time only with his pulse. Yes. And he arrived though on those conclusions of equations of motion by simply approximating, okay, even though the pulse changes, but in the normal time it's the same. But sand is something which takes some time. The pulse is roughly 1 second. Can you imagine that? थोड़ा सा 40-50 उम्र का जो आदमी है उसका हार्ट रेट थोड़ा स्लो होता है. फर्क है मेरी उम्र का बंदा जो है जो नॉर्मल रेट है 70 बीट्स पर मिनट. अगर 45-50 में चला जाए, it's about 60 beats per minute. So, and it was quick enough that you can observe the falling and moving bodies with that. Anyway, so the time measurements were crude, and the things were so coarse that even if there was some change in time in a moving train and on a person on a horse, you can detect that. So you can forgive people for assuming that this was true. So this was actually the bedrock of physics until 1905. And this consequence that the velocities should add was reigning supreme. And it was used to measure and do all those things. You can measure trajectories of projectiles. You can predict that if you fire a cannonball, where it will go. And although if you fire it from a moving cord, what would be its trajectory? All those things were being done by this assumption. Until people started measuring the speed of light. And when Michelson and Morley, they wanted to actually measure the speed of light and do more than this, because there was another problem in the 19th century physics, which was if the ether exists or not. Ether. So Maxwell had this idea that light is electromagnetic wave, and people knew that for wave to travel, you have to have a medium. And to show that, people were trying to measure the speed of light, because you see the Earth, this is Earth, so this rotates. So it means that the sunlight that is coming from here, when it is coming from here, if you measure its speed while you are standing at Earth, you should measure differently when the sunlight is coming from here, right? Because the speeds have to, and if you are moving like this, and the sunlight is coming from here, according to the law of velocity addition, you should measure the speed of light as c plus v, because you are going towards it. It's like if a bullet is coming towards me and I'm running towards the bullet, the speed of the bullet with respect to me is now the bullet speed plus my speed. And if I'm running away, the speed is the difference. So that's what Michelson was trying to do by measuring the speed of light in orthogonal direction, because he was actually trying to prove the existence of ether. But what he found, that even though the Earth moves by roughly 86,000 meters per second in this medium, there's no change in speed of light. You point your telescope this way, and you point your telescope this way, the speed is the same. So either Michelson is doing something wrong, what Galileo taught us 400 years ago was not right. So that was the impasse that Einstein solved by saying that Galileo's first idea is not correct. He still believed in the second principle, that the laws of physics should have the same form, but he discarded this first idea, and that was the birth of the special theory of relativity that we will take up in the next lecture. Yes, there was a question?